Hello, welcome back to Physics 211. We have been looking at currents and resistance, and we've seen that currents are directly related to the potential difference by Y1 over the resistance. And we've seen that we can, if we write that as V equals IR, that is Ohm's law. And we can say, we remember that by thinking when we're cold, we say ver. And now we're going to look at some applications of Ohm's law. And we're going to start by looking at if we have a battery, just a simple battery with a wire between it. So let's start by looking at a battery. We know that a battery is a source of potential difference. So it's giving us a source of our potential difference, delta V sub bat. And so if we have our battery attached to just a simple wire, we have our positive terminal where our potential energy will be equal to the charge times delta V bat, battery. And as we go along our wire, we have decreasing potential energy as we go along our wire, and we get to our negative terminal where at this point our potential energy will be equal to 0. So the charge itself falls downhill through the wire, going from positive potential energy all the way down to 0 potential energy. But a current can be sustained because of the charge escalator. So the charge is moving our charges up within the batteries. So the batteries supplying this source of increasing potential energy. And the charge escalator is lifting our charge from the negative side to the positive side, where the charge, little q, gains energy, delta U, that's our change in our potential energy. And so that's going to be equal to so a change in the potential energy will be equal to our charge times our delta V. So when the battery creates a potential difference between the ends of the wire, we're able to start having our current going along our wire. And so the potential difference in the wire creates an electric field in the wire because we have this potential difference within our wire. And that electric field pushes a current I through the wire in the same direction as the electric field, which is not the direction that the electrons are moving. And we know that that current in the wire is going to be related to the potential difference by Ohm's law, Ver, which we can also write as the current equals delta V wire over R, the resistance. So let's look at Ohm's law. Now, Ohm's law is limited to those materials whose resistance R remains constant or very nearly so during use. So it has to be something where the resistance isn't going to change. And otherwise it's not, and those kind of materials, we call them ohmic. So they're ohmic if their resistance remains constant or close to constant during use. So things like metals and other conductors are ohmic devices. That means that their resistance remains constant and they have that nice linear relationship. So the current through an ohmic material is directly proportional, has a nice linear relationship to the potential difference. So it will double so doubling the potential difference doubles the current. They're directly related. And if we plotted those, if we plot the current here on our y-axis and our delta V over here on our x-axis, we know that our current equals 1 over R delta V. So since I, our current, is our y in this case, and delta V is our x, 1 over R is our slope of our line. And so we see that the slope of the line is 1 over R, or it's written here as the resistance is equal to 1 over the slope. And so that shows us that because we have this linear relationship, the current is directly proportional to the potential difference. Now, some materials and devices are they don't have that nice relationship. They're non-ohmic, meaning that the current through the device is not directly proportional to the potential difference. Things like diodes, batteries, and capacitors are all non-ohmic devices. That means that we don't get a nice linear relationship. So here's an example of a non-ohmic material. So if it's a non-ohmic, it means that it's not directly proportional, not linear. So we end up with a non-linear relationship. So this curve is not linear and does not have a constant slope. And so these are non-ohmic materials. All right, let's look at an example of a battery with a wire and a resistor, and just a simple circuit where we have a battery. There's our battery right here. Here's our battery. And our battery is connected, has a wire connecting the positive terminal to the negative terminal. And then within that circuit, we have a resistor. So this is our simple circuit where we have just one resistor. So the current must be conserved. So hence the current I through the resistor is the same as the current in each wire. So I on this side must be the same as I over here in this circuit. Current is conserved. So the current is constant through each wire. So now if we want to plot what happens with the potential difference in our circuit, we can plot what happens to that potential difference as the current goes around our circuit. So as the current goes around the circuit, this is the distance around the circuit. We saw it first went through the wire. So as it goes through the wire, if it's an ideal wire, so we call it an ideal wire, we assume there's no resistance. And it's not totally completely true with any real wire, but we usually make the assumption that our wires are ideal, so they have no resistance. So if there's no resistance, then there is no voltage drop along the wires. So it would just be a constant line as we're going along the wire. So then once it gets to the resistor, once we get to the resistor, then we have a voltage drop. So now we're going from whatever the initial voltage was from our battery, and we have our voltage drop across the resistor. And that voltage drop, and then we get back to our wire where we don't have any change. But the voltage drop across the resistor must be equal to the voltage drop across the battery if all we have is that one resistor, because the total voltage drop, as we know from Kirchhoff's loop law, around our circuit, our total voltage drop must come back to zero. So the total voltage drop around the circuit must be equal to the voltage drop across the battery. So if I put these two next to each other, here's our circuit, our image of our circuit, or schematic for our circuit, where we have our battery. And over here, we have our wire that's lining up here with this piece of wire going from the battery to the start of our resistor is right here. We see that there is no voltage drop across the battery. And then we go across the resistor. When we go across the resistor, we do have our voltage drop. And that voltage drop, again, is equal to the voltage drop across the battery. And then we go along the wire, and there is no voltage drop, so the voltage is constant. So that is what we have when we have a circuit where the resistor, as we see in this circuit, is ohmic. So we get a nice slope as we have a nice voltage drop across our resistor. So that is an example of using Ohm's law and some of Kirchhoff's laws to understand the current and the voltage drop in a circuit.